All right, guys. I'm going to try to talk about grav. I don't even know if I spelled that right. Gravitational field strength. And so let's just think. Ivy talks to you about that it's measured in newtons per kilogram. And so gravitational field strength is just what is the strength of that field at a given point in space. So, and then we also recall that we're going to treat spherical masses as point masses. So if you shrink all this down to a point, then all of its mass will be centered there. And so in other words, they're just telling you to use the you need to measure to the center of the sphere, not just to the surface. Is a good way to think about that as well. And then you always treat it like a point. So if you put a person here on the Earth, and then you were to use the Newton's law of universal gravitation, G m1 m2 over r squared, where r is the radius from that person to the center of the Earth, then you would find out that when you found the force between these two, if you knew m1 and m2 and r squared, and you know g because it's a constant, then you'd find out that the force is equal to their weight. But if you think about what weight is just m, their mass, times g. And that g happens to be g just for Earth. But it could be g for anything, anywhere. You could say, what is g on Saturn? You could say, oh, it's 9 Earth G's, so 9 G's. So we know what G is of Earth, so we can explain it in terms of Earth, G's of Earth. So that means if I'd like for you to think about this, if you put in m1 G equal to G m1 m2 over r squared, the m1's cancel, and that leaves you with the gravitational field strength in G. Now, if you look at this set of units right here, this is nothing more than the units of acceleration, because a Newton is a kilogram times a meter per second squared, and then you divide it, that's per kilogram, so over kilogram, and then the kilograms cancel out. So when they give you a G value for a planet, they're actually giving you the gravitational field strength for that planet and how many newtons would pull on a 1 kilogram mass in that particular case. But I also want to point out this right here. I'm going to try to use a different color. If you take these numbers and do the math with them, you end up getting, for Earth, if you choose for Earth, you end up getting negative, around 10 meters per second squared, and which basically is that number. So what they're saying is that this equation right here is merely just these three numbers, tick, tick, and tick. Those three numbers, and you've already done all the math with it, and they give you back G. So that's why you're actually using this equation, but you're pulling out all the constants. What are all the constants? What are all the constants? Well, Earth is a constant. The radius of Earth is a constant, and G, big G, capital G, is a constant. So why don't we just go ahead and make those into one small value, and then we'll plug it in, and whatever mass we have, guess what? We now know the force between the two. We know that, and we call that its weight. So that's what they're talking about there. Let's just pull out the constants, make it an easier number to work with, and that's universal. That's gravitational field strength. So. Well, not particularly. So now let's just talk about this. So what if I said, hey, I want you to measure out to here? Well, heck, now if I know R here, and I know the mass of Earth still, I can now find the gravitational field strength in newtons per kilogram there. Oh, okay, but what about here, over here? Then if you know R to there, you can find the gravitational field strength there. And what you see is that as that R increases, the gravitational field strength is going to decrease, or the number of newtons pulling on a given kilogram is going to decrease in magnitude. But the direction would always be the same. And that gets me to having you think about one more thing. Remember, it's a field, and the direction. So just to get back to that, this is our mass. Okay, and the arrows, the field vectors would be going towards it. And so as I wrap up with this to get under hopefully just over 5 minutes, the one last thing is to remember is that it's a field, and fields are vectors. So that you can treat them as vectors once you find them. So once you find the gravitational field strength, you can treat it as a vector. And that makes it easy to work with once you find the x and y components. And then you just add it the way we've been adding vectors all along. All right, so we'll stop with that. I hope that helps you get a little bit more understanding of gravitational field strength.